Okay, I just handed out the homework number 4. So I gave one problem per each topic that we covered after midterm. So the first one is three-dimensional potential flow. And here, as I said in the problem, you are supposed to use a 3D source potential and basically derive the equation that I wrote. Okay, equation number 1. Number 2 is boundary layer theory for the free surface boundary condition. Probably you have to think a little bit to get the solution, the answer that I asked you find. But it should be okay. And the third one is the linear dispersion relation for a two-layer system. So this time you have two fluid of different densities, rho 1 and rho 2. And the thickness of each layer is H1 and H2. Okay, and then the top and bottom boundaries are rigid boundaries, and there is only one interface between two fluids. So the boundary conditions that we discussed for a single layer can be extended. The only difference is, the dynamic boundary condition where you impose, continuity of pressure. Okay, this time, we neglect viscosity. Okay, so for a single layer case, you assume pressure is 0 because you neglect, the motion of the upper fluid. But this time, the density of the upper fluid is not negligible, so you have to consider, both fluids. Okay. But again, we assume ideal fluid. So you solve Laplace equation in each layer and then impose, the appropriate boundary conditions. I noticed that there will be no class on May 5th and May 10th because of international holidays. So due is May 12th, which is Thursday, so 2 weeks from today. Okay, so you have plenty of time to do. Also, we have to decide, the final exam date. I don't know what you prefer, but I suggest, the Tuesday of the final exam week, which is May 24th. So final exam week starts on May 23rd and for a week. So I'm suggesting, the Tuesday, the second day of the exam week. So May 24th. Any objection, or is it okay with everyone? I'll give the final exam exactly the same format as you did for the midterm. Okay. On Tuesday, I mostly discussed the phase speed. So we start with dispersion relation. Dispersion relation between frequency omega and the wave number k. And for gravity waves, we have as I said earlier, we called the waves that we are looking at are gravity waves because the restoring force is gravity. So if you lift free surface, if you let it go, the surface goes down because of gravity. Okay, so that's why the free surface is fluctuating, and so for gravity waves, this is a dispersion relation. Omega is wave frequency, which is defined 2 pi divided by period, right? And k is wave number, which is 2 pi divided by wavelength lambda. And h is water depth. And from here, we can find the phase speed, c, which is defined by basically length divided by time. Here, the length is a wavelength, and the time is a period. And in terms of omega and k, we can write this in this way. Okay. So this time we have plus and minus g over k like this, because I have to divide by k squared, which is c squared, and then I have to take a square root. So we are looking at the surface elevation like a e to the I kx minus omega t, right? And then e to the I k x minus omega divided by kt. And this is nothing but phase speed, c. So this is exactly the speed of phase at which phase is propagating. And so this is the gravity waves are dispersive because c is a function of k. Okay, depending on wave number or depending on wavelength, the speed of phase speed changes. And so, for example, if you look at for infinity deep water, for deep water, c is nothing but plus minus square root of gk. Here, no, sorry, square root of g divided by k. Because, as h goes to infinity, this is 1, so I have g divided by k, and so this is nothing but plus minus g lambda 2 pi, because k is lambda divided by 2 pi, 2 pi divided by lambda. So from here, it's obvious, right? C, as the lambda increases, c increases. So the longer waves travel faster. So 100 meter wave is moving faster than the 1 meter wave. Okay. But on the other hand, for shallow water, for which h goes to 0, c is square root plus minus square root of gh, because the hyperbolic tangent kh behaves like a kh, so k cancels out and then you end up with gh. So this is independent of lambda, so this is non-dispersive. Dispersive. So the wave speed, since wave speed depends on the wavelength, typically water waves make a group in which the wavelength of waves are similar. Okay, so suppose you have many different waves at one location, and if let them propagate, and some propagate faster and some propagate slower. So if you here you see only faster waves, and later you see some slower waves. So the waves make a group between waves of similar wavelengths, and then they travel together. Okay. That's what I'm going to describe a little later. But anyway, so these are the important the fact. And finite depth also, waves in finite water of finite depth are also dispersive because it depends on wave k and therefore lambda. If you plot c square root of gh here and versus kh, what happens? So 0, I have 1 because c is square root of gh, then I'll decay like that. Okay. And I have a plus and minus because I have waves propagating to the right and waves propagating to the left. Okay. Okay. So the phase speed is important because it tells where the crest is and where the trough is. Okay. So if you have a wave, then you can tell where the crest is later because this crest is moving with the phase speed c. Okay. And but there is another concept, as I just mentioned, which is group velocity. So to explain what the group velocity is, I have to show one thing. Let's say in ocean, right? In the ocean, there are many wave components, but let's say we have a two wave component, and which is a we are talking about linear waves, right? So I can superimpose two linear waves. They are also linear waves, okay? And here I assume K1 and K2 are not so different. A K1 is given by that, and K2 is this. So here, my delta K over K naught is very, very small. Okay. Which means I add two waves whose wavelengths are very similar. Okay, because wave numbers are very are close to each other. Okay, because delta K is much smaller than K naught. So in this scenario, when you add two waves with a similar wavelength, and we are interested in how they propagate. If you have only a single wave, what happens? Single frequency wave, then this guy just propagate, right? Without change of form, they just travel with the speed c. Okay? But if I add two waves whose wavelengths are very close to each other, then let's see what happens. Once I fix wave numbers, frequencies are fixed through dispersion relation. They are not arbitrary. So I can compute dispersion relation in this way. I know the functional relationship between omega and k through the dispersion relation, okay? So I'm evaluating that function over there at k naught plus delta k, which is k1. And then I said this guy is much smaller than this guy, therefore I can do the Taylor expansion. So let's do that. And then dk, no, d omega dk. I have to evaluate a k naught and times delta k. Of course, I can continue. And that term that I didn't write is the order of delta k squared. So delta k is small, then this is very, very small. So my shorthand notation is omega naught. So this I call omega naught. And this one I call omega prime naught, because I'm taking first derivative, delta k. So this is just the shorthand notation of this guy. And then I dropped, all the delta k squared. If I look at the omega 2, so this is omega 1, and omega 2 can be found by evaluating frequency dispersion relation at k equal to k2, and then k2 is k naught minus delta k. Once again, this guy is smaller than this. I can expand. Minus d omega dk k naught delta k. Of course, I neglect delta k squared term. And then I can write this as omega naught minus omega naught prime delta k. Okay. So now I know the expression for omega 1 and omega 2, and therefore I can rewrite this. So zeta is given by A is the same. So I pull out. Then I have e to the I. K1 is k naught plus delta k x, correct? And then I have minus omega 1, which is this, omega naught plus omega naught prime delta k t. Of course, I neglect the higher order terms. And then I have e to the I. Now I am adding this term. K2 is k naught minus delta k x. This is k2x minus omega 2, which is omega naught, as I can see here, omega naught prime delta k t. So this is just omega 1, and this is omega 2. Now I have a common factor here. So I can pull out. And so we have zeta as A. I pull out this because I have here and there, I have this guy. And then I have, what do I have? E to the I delta kx minus, let me pull out delta k as well. Delta k here, x minus omega naught prime t. That's the first term. So I have a delta k here, sitting here and here. And then I have plus e to the minus I delta k, x minus omega naught prime t. Okay? I didn't do anything fancy. I just pull out, the common factors, and that's what I end up with. Now, this guy is, by definition, 2 cosine delta k x minus omega naught t. Okay? Because cosine x is e to the I x plus e to the minus I x divided by 2. That's what the definition of cosine x. So this guy is this. So I can rewrite this as 2a cosine delta k x minus omega naught prime t and e to the I k naught x minus omega naught t. So compare this with surface elevation for single frequency, which is okay. So almost that looks like this, except that this part is a function of x and t. Okay? So over there, this amplitude is constant, and this time, this amplitude is not constant. I still have e to the I k naught x minus omega naught t as over there, and then but this part, which I call A, is a function of x and t. So instead of having constant amplitude like that, you have, the amplitude which depends on space and time, but in a very special way. Okay. So I'm plotting this part is 2a cosine delta k x minus omega naught prime t. Okay, that's what I'm plotting. So previously, the amplitude was constant, a, or specifically I can say a naught. Instead of having constant amplitude, I have an amplitude which depends on space. Okay? Single frequency case, I have constant amplitude, and then I have waves like that. Correct? That's what happens, right? This time, my amplitude changes. So what I have, sorry, this is has to be here because I'm plotting cosine. Okay. what happens is, so I have to draw. So what happens is this. So instead of having constant amplitude wave, you see wave amplitude changes, but it modulated. And this, dashed line is called the wave envelope. Okay, because the waves inside are trapped by this, wave envelope. Okay, and these are called carrier waves. The waves inside of the envelope. And then this envelope is moving. This envelope is moving with a speed, what? Omega naught prime. That's the speed. So I didn't do much. I just added, two waves. But, whose wave numbers are very close to each other. And then I see, instead of constant, the envelope, I see slowly varying the wave envelope. Okay. Of course, from here to here, this length is 2 pi divided by delta k. Because I'm plotting, cosine delta kx minus omega naught, omega prime t. So this is this envelope is 2 pi divided by k, delta k. And also, or wave number is delta k. And what you can see is, which one is bigger? 2 pi divided by delta k and 2 pi divided by k naught. I said delta k is much smaller than k naught. So this is much smaller than this. Therefore, this guy is much bigger than this, right? Because the denominator is much smaller. Meaning that the variation of envelope or amplitude is much slower than variation of the carrier waves. Okay. So the envelope is really slowly varying compared with this guy. This guy is moving faster because the wave length is shorter. So you see a highly highly fluctuating part inside. But if you look at the envelope changes slowly. Okay. And then this envelope is moving with the group velocity, this velocity, which we call group velocity. So here we have first the definition of group velocity. which is d omega dk. So whenever we have two waves of similar wave numbers or similar wavelengths, they form a group, like this group. This is group. Okay, they move as a group, not like this. Okay, and of course you don't see this dotted line in the ocean. What you see is this guy. The solid line. You don't see, the dashed line, but you can, once you have, the solid line, you can draw dashed line, and then I said this is the envelope. Yeah. And that envelope travels with the group velocity. Now, this envelope is moving, whole thing is moving. K waves are also moving. K waves are moving with the speed of phase. So which one is moving faster, envelope or carrier waves? Envelope is moving group velocity, and carrier waves moving phase velocity. Sorry, I haven't talked about the definition of group velocity. So let me say that first, and then I'll ask you that question again. So group velocity is defined in this way, and now to find that, we start with the dispersion relation. Okay, I'm trying to get the definition of group velocity from here. So what I'm doing here is I'm taking the first derivative with respect to k. So what I get is 2 omega, and then d omega dk, right? Omega is a function of k. So I'm taking k derivative here. So this is linear dispersion relation. I'm taking k derivative. And the left-hand side is 2 omega d omega dk, which is a chain rule. And then I'm taking k derivative here on the right-hand side. And then g, hyperbolic tangent kh, because I'm taking k derivative. And then I'm taking k derivative here, and which is g times k. And then I'm taking k derivative h, and the derivative of hyperbolic tangent is h squared, okay? So from here, what we can see is okay, let me write d omega dk here, and then I have g divided by 2 omega, okay? And then which one do I have to pull? Okay, let me pull out hyperbolic tangent kh here, and then I have 1 plus kh. I pull out g hyperbolic tangent kh, and then I have kh, and then what do I get? 1 over hyperbolic cosine kh here. That's the definition of h squared, right? And I pull out, okay, so I have that's what I end up with. And so this part from linear dispersion relation, this g times hyperbolic tangent kh is nothing but omega squared divided by k. And so I can rewrite this. So I have 2 omega in the denominator. And the g times hyperbolic tangent kh is omega squared divided by k. Because omega squared is gk hyperbolic tangent kh. And then I have 1 plus 2kh times 2 cosine, hyperbolic cosine kh, hyperbolic sine kh. I just multiply the numerator and denominator by 2. And then what I end up with 1/2 omega divided by k, 1 plus 2kh divided by hyperbolic sine 2kh. That's the definition of hyperbolic sine 2kh. So finally, I got the expression for group velocity. So group velocity is given by 1/2 omega divided by k, 1 plus 2kh. Or I can write this as 1/2 times c, because omega divided by k is a phase velocity. And okay, because this is a phase velocity by definition. So let's see how big this guy is. As kh goes to infinity, deep order, then what happens? Hyperbolic sine increases much faster than 2kh. Hyperbolic sine 2kh is increasing much faster exponentially. And therefore, this guy goes to 0. And my group velocity is just half of phase velocity. Okay? On the other hand, as kh goes to 0, group velocity is equal to hyperbolic sine x is x for small x. So this is exactly the same thing. And then I have 1 plus 1. And therefore, I have a 2 here. Then this is c. Here I use hyperbolic sine x behaves like x. Okay. For small x. So what it says here is for shallow water, group velocity is the same as phase velocity. But as h increases from 0 to some value for finite depth, group velocity is smaller than phase velocity. And infinite depth, group velocity is just half of phase velocity. Okay? So group velocity is smaller than phase velocity. Okay? So this is what you have to remember is for gravity waves, so let me write down. For gravity waves, group velocity is always less than phase velocity. Of course, they are equal when h is 0, but there is no the case where h is 0. So group velocity is always smaller than phase velocity. So group velocity is the d omega dk, that's the definition. And then group velocity is smaller than phase velocity. So now now let me go back to the question that I asked. Group velocity is slower than phase velocity. And then what happens here? So at one time, right? So these are the envelope, and the waves are moving like this, right? So let me pick, this crust, let's say A. As time goes on, this guy is not stationary. Even though the crust is moving, this guy is moving faster. But this guy is not moving with a constant amplitude. The amplitude decays, but moving faster than group velocity. Okay, so a little later, I draw exactly the same thing. Because the envelope is moving with a constant speed. I should draw this. I went too far. But my point is the following. If the whole thing is moving, the envelope is moving with the group velocity, and then at a later time, the A would be here. Like that, okay? So this point A, at a later time, is still moving faster than group velocity. So this guy is ahead of the position here, okay? But the amplitude is decaying. And when A reaches, this point, amplitude is 0. So although phase is moving faster than group, the envelope, they cannot travel further. It decays. So this carrier wave goes past, this point, the crest of envelope, and then decays. And then the next one growing and decaying, and that kind of thing. Can you see that or not? So my point is, this crest and this crest are not moving with the same speed. This crest and this crest, I'm talking about crest of envelope and crest of individual carrier wave, they are moving different speed. Okay, that's if you don't see it clearly, that's what you have to know. Okay. And then the distance between here and here will increase because this guy is moving faster than this guy. So this guy is moving, but the front guy is moving faster. Okay? So the distance increases. But this guy cannot travel in this way. This guy has the amplitude of this guy decays as they travel. Okay? So that's why you always maintain this group structure, this envelope. In reality, if you take the snapshot, so if you take a picture of real ocean, you often see something like this. That's quite a common feature that you see. So this is space, and this is surface elevation. In real ocean, you see the envelope. like this. This is a very common, the snapshot of surface elevation or waves in the real ocean. Okay. And here, I just add 2 waves with a similar, wave numbers. In the real ocean, there are many different, wave numbers, different waves. There are many waves of different wave numbers. And, but they make a group here. And inside of group, the wave numbers are very close to each other. And here, in this group, the waves inside have a different, similar, wave numbers. So they form a group, and then they travel. And this envelope travels with the group velocity, although individual phase is moving with the phase speed. But this phase cannot travel beyond, this individual crest cannot pass, cannot escape from this group because amplitude decays. Although crest is moving faster, but amplitude decays. So they stay inside of this, the group. Okay. So the example that I often, use is the following. When you have a group of students, right, walking to the, restaurant for lunch, and then at the beginning, everyone is in the same pack, right? So let's go to lunch. But as time goes on, you see group. Of course, if you know someone better, you follow, the other guy. But in general, what happens is, the faster guys, go ahead of other guys who are slower. So you make groups of different speed. That's what happens, when you go to lunch as a group. Okay, just like that. Waves, each wave has a different wavelength, therefore different wave speed. So when you put all the waves put together in one position, then they don't move as a pack. No. Because each one moves in a different speed, then at the end, of course, at the beginning, they move. But as time goes on, the distance between the groups increases, and these guys are, move faster, and in other words, they have a longer wavelengths. Because in longer waves, travel faster. So at the end, they make a group, and this is a group. Okay. And in each group, the wave numbers are, similar. So waves inside of groups have a similar wave numbers. This happens, groupiness happens because waves are dispersive. In other words, waves of different lengths have a different wave speed. For example, if wave speeds are the same, independent of wavelengths, then what happens? If you put all the waves at one point, they move exactly the same way. The shape will be exactly the same. Okay? So that's the difference between dispersive and non-dispersive waves. So let me emphasize one more time. So this is my mean surface. Okay, so this is a mean free surface. Suppose I lift a free surface like this. Okay, I lift it. I let it go. Then this guy has many different wave components. It's not just sine wave, right? To make this wave, you have to add many different Fourier components to make this shape. So meaning that I add many different waves here to form this surface elevation. So I lift it and then let it go. And since there are many different wave components, each wave component travels different speed. And at the end, as I said, later if you see, you will see the group. This group travels faster because they have a longer wavelengths. Actually, to be more precise, this length, this is a wavelength, right? This wavelength has to be smaller. Wavelength here, crest to crest, will be smaller than this length because this has a longer wavelength and they travel faster. Okay. But for shallow water, if this happens, then what do you expect? Later time, they travel together. Even though they have many different wavelengths, the wave speed doesn't depend on length, non-dispersive. So they travel together all the time. Okay? So that's why tsunami, once it is formed in the shallow water, they travel together. Okay? So that's the difference between the waves in deep water and in shallow water. Okay. So the most important thing is, since waves are dispersive, ocean waves, always form a group. Okay? Group of waves of, similar wavelengths and therefore similar wave speeds. So that's one definition of group velocity. To talk about second definition of group velocity, I have to talk about energy. Wave energy. Since we are talking about two-dimensional waves, the energy, what I'm really talking about is energy per wavelength, or per length. So this time I have a kinetic energy plus potential energy. Okay. So I call it kinetic energy and potential energy. And kinetic energy is defined by from 0 to lambda. So I'm looking at one wavelength. And then I have to integrate from minus h to zeta. Velocity is 1/2 u squared plus w squared, right? So which is phi x squared plus phi z squared dz dx. I can multiply by rho, but rho is constant, so I just let me put it. So this is a energy density. So this is a rho 1/2 rho times u squared plus w squared, velocity squared. I have to integrate over volume, then I will get mass times velocity squared, which is the dimension of energy. And this time we are looking at just two-dimensional flow. I neglect, variation in the y direction, so I didn't integrate in y direction. That's why I'm saying, energy per length, okay? But anyway, so now we know the expression for phi x and phi z. We can plug in here, and then we integrate it, okay? But this time, instead of integrating from minus h to zeta, I'm integrating minus h to 0. Linearization again. So this whole kinetic energy is a function of zeta because I'm integrating from minus h to zeta. And since the zeta is small, I can expand this guy like this. And I neglect all higher order terms. I'm just looking at the leading order term. In other words, I just replace the upper limit of this integration by 0. Okay. So in other words, I'm integrating the velocity field squared from minus h. I'm supposed to integrate all the way to zeta, but my zeta is so small, I'm integrating only up to z equal to 0. That's my linearization, okay? So since we know the expression here and here, we can substitute it and then integrate with respect to z, and then we integrate with respect to x as well. So suppose we do that. So here the velocity potential is c times a. Hyperbolic sine kh, and then e to the I. If you want, you can put sine kx minus omega t. And then mean kinetic energy density is defined like 1 over lambda kinetic energy. Okay, so here I'm just taking, I'm taking the mean here, and then I divide by 1 over lambda. Okay, so I often write the kinetic energy over bar, over line, and the lambda here, meaning that I'm integrating this quantity and then divided by lambda. So at the end, this is energy per area, okay, and which I call energy density. Energy density. So if I want to know the energy per one wavelength, then I multiply by lambda, then I'll get the energy in one wavelength. Okay? And this guy, when you substitute everything here, then I end up with, I'm not going to show the whole detail because I don't have time. That will end up with this. Okay? Quarter times rho g a squared. On the other hand, I can do exactly the same thing for potential energy. But I'm taking the mean over one wavelength, which means I'm dividing the potential energy per wavelength. So I'll get this from 0 to lambda and minus h to zeta rho g z dz dx. So once again, the potential energy is, for particle, mgh, right? So here I have rho gh, basically the length. And therefore I have to multiply by integrate over volume. But since I'm looking at two-dimensional, flow, I'm just integrating over x and z. And then I'm taking average over lambda. So, but to do that, once again, here, when you do the disintegration, you end up with exactly the same thing. Okay? And at this time, instead of having from minus h to zeta, I'm integrating from 0 to zeta because I have a wave here, and I'm only interested in potential energy due to the variation of surface, and I neglect, this part. Okay, so that's why I replace in a lower limit by 0, and when you do plug in and then you just integrate it and taking the average, you end up with this. So this is once again energy density. And so total energy density is given by, okay, quarter rho g a squared plus quarter rho g a squared, and then I end up with 1/2 rho g a squared. So this is a wave energy per area. So if you have waves like this, and this is a unit area, this is the energy contained in this column. Okay? So inside of this column, I have 1/2 rho g a squared. That's the density. If my area is 1, then this is what you have. So if you know the area that you are interested in, then you know how much energy is contained in that area. Okay. And another thing of interest is this part, potential energy part and kinetic energy part are exactly the same. So this is called the equipartition of energy, meaning that kinetic energy is exactly the same as So someone asks you to find the energy contained in one wavelength. then what we have to do is 1/2 rho g a squared times lambda. That's the energy per length this time, right? Because you neglect this part. If you know the length of this part is supposed to be, then this is the energy contained, wave energy contained in that area. So if you look at from the top, this is lambda, this is x, and this is y. And this time this is x, and this is z, right? And this is lambda, and this is b. And this is lambda. If you want to know the energy contained in this area, that's exactly what you have. Okay? So that's the energy contained in this column. One thing important is that this guy, the energy density is independent of omega, A, or H. No, I'm sorry. Independent of omega, K, or H. It only depends on wave amplitude. Okay, that's the one thing that you have to remember. So more specifically, let me put here. This is total energy. Total energy per wavelength in one. This is total energy per unit area. That's what the energy density is. To make the second definition of group velocity, I have to go through the energy flux and so on. But it will take a while to. I don't have much, enough time to go through it, and so I'll do that, next week. Otherwise, I have to, hurry. But basically, what I'm going to show later is energy flux is mean energy density times, group velocity. So meaning that the group velocity is the velocity, the speed of energy transfer. That's what I want to show. Okay. So the first definition of the group velocity is the group velocity is the speed of an envelope. That's one definition. And the second definition, which is independent of the first definition, is the group velocity is the speed at which energy transfers. Okay, so that's the useful concept later. So I want to go through that, but I don't have much time today. So today I'm going to finish a little early, but I'll do the discussion. I'll do the discussion for the energy transfer in the next class. Okay.